Hello, and welcome to my presentation on item response theory. So getting into it, what is the application context of item response theory, right? Like where are we applying something like this? So as the name implies, we have items that we're responding to, and what we want to do is obtain some latent parameter describing each individual student or subject taking these like exams or questionnaires to to obtain some value and compare them with one another or some threshold. And so before jumping into item response theory, I think it's good to define or gain some intuition about what the logistic function is because this model is based entirely off of it. So taking a look at the top right here, this is the definition for the logistic function. And the way we can derive it is if we have, let's just say we take this case of two of these Galton boards. What they have is like a bead that comes down here. And if you have many of these beads, it ends up forming a normal distribution. And if we have two of them together, right, and we take one of these bins here and we say, okay, what's the probability that a ball in this bin here, like given it's in this bin here, right, which is our x value, what is the probability that it came from this right container here, right? What is the probability that it came from the right container given x? And so following Bayes' theorem, this directly leads us into the logistic function. And thus we can interpret it as this kind of probability of an event happening. And so first things first with item response theory, we need to jump into the postulates and assumptions. So for the postulates, we have predictability and a monotonic increasing item characteristic curve. So for predictability, that means that there must just be latent traits that exist that can predict the subject's performance, as well as for the monotonic item characteristic curve, it's just defining that there must be some curve related to the performance of the subject such that it is always increasing. So if a subject increases in their performance, then that means their ability or their predicted ability should increase as well. And this is exactly why we use the logistic function, because it describes exactly this. It is our item characteristic curve. As well as for our assumptions, these are things that we need to make sure that we check to ensure that they are true, right? Because our postulates can always be taken to be true. For our assumptions, we have two: unidimensionality and local independence. So unidimensionality, uni means one, dimension means a dimension or a parameter, means that there must be only one parameter that describes a subject's ability. So it can't be two, can't be three, can't be anything. It can only just be one. And as well as there's also the assumption of local independence, which just means that each observation taken is independent from one another. They don't affect one another, which means that it's only the parameters of our model that are describing the ability of a subject. So jumping into some item response theory models, it seems like a lot, but these are all just built off of one another. So starting at the very top, we have the one parameter logistic model, which is also called the Rasch model. And so you can see here, it's basically our logistic function, but we have these two parameters here. We have theta, which we can define as the subject's ability to perform on maybe answering some question. And we also have the difficulty of a specific question, right? And so if you see here, if we have a difficulty of a question matching the subject's ability, then we would expect a 50% chance that a subject would get an item right. And if the subject has way more ability than the question is just very easy, almost guaranteed to get almost guaranteed to get the answer right. And if they're lacking in ability, they're almost guaranteed to get it wrong. As for our two parameter logistic, all we're doing is just adding this other parameter, delta here for each ith function, or for each ith question. And this delta is the discriminability, because this will affect the slope of our logistic curve, which means that for this theta minus d parameter that's very close to zero, then these questions will be able to discriminate between cases like that. And then for our three parameter logistic model, all we're adding is this term out here, which its entire purpose, what it's doing is that it's adding a lower bound to our logistic. And how we can interpret this is basically the probability of guessing and getting a question correct. So if we're doing a multiple choice test with 4 questions, right, then we would expect the C value for this case to be 0.25. Right? So if a subject has very, very low ability and they just guess a question, this term will end up being 0 and we're left with 0.25. And so there's around a 25% chance that a subject will get a question correct in this case. And for the 4 parameter logistic model, all we're doing is adding an upper bound here, L. And what this upper bound, how it's interpreted, is to account for any careless mistakes someone with a higher performing ability might make. Because we don't want to assume that they're going to guarantee to get a question right 100% of the time. They might just misread something or kind of skip over some information. So an important assumption with this as well is that all these models are just for binary responses, right? Right, wrong, yes, no. But there are some models that exist for non-binary responses, but we're not going to go over those. And so where does item response theory apply to exactly? There's some studies on its application for psychological assessment. And so looking at these 2 studies here by Anderson and Miller, as well as Zanon et al., there's a pretty similar path that they follow, or methodology that they follow, in which they're gathering item response data. And then once they gather that data, they're then confirming the assumptions of item response theory for that data. Because remember, we must make sure that our assumptions hold. These need to be checked. Unidimensionality and local independence. These must be checked for our data. And so once we do confirm that our assumptions hold, then they can fit the data using their choice of item response theory model. And then from this model, they're able to get parameters in order to obtain a test information function and standard errors. And then from that, that's able to tell them what needs to be, like how to modify a test in order to get better results that they want, or maybe remove any redundant features or redundant questions of a test. And so now jumping into a possible application that, say, I can use item response theory for, because I found it very interesting from this paper from Stivers et al. 2022, in which they were measuring the accuracy of groups in observing correct objects in noisy images, and where they had human-human pairings, human-machine pairings, and machine-machine pairings. I thought it'd be interesting to try to apply item response theory, maybe in this case the 4PL or 4 parameter logistic model to and have a hierarchical extension to it, because we assume that these pairings of people maybe come from the same distribution, or their latent parameters come from the same distribution. And so we would use this hierarchical extension in order to maybe compare these pairings using that latent parameter obtained from item response theory, rather than just looking at the accuracy here. And so there are some tools that can help assist with that. One that I found is PyIRT. And so, yeah, it'd be very interesting to see how this comparison looks like if things do change or don't change. And yeah, that's basically it. These are my references. And while I scroll through things, thank you so much for listening to my presentation and for the quarter. So yeah, thank you.